This video is sponsored by Squarespace, the Albert Einstein of website builders. You've probably been taught that Einstein introduced the idea that light is made of particles so that he could explain the photoelectric effect. But that's not really how it happened. The real story began with a crisis in physics. At the end of the 19th century, physicists thought they understood light. James Clerk Maxwell's electromagnetic theory had unified optics, electricity, and magnetism into a single astonishingly successful framework. According to this framework, light was an electromagnetic wave, an oscillating electric and magnetic field that was smooth, continuous, and spread out in space. Phenomena such as interference and diffraction seemed to confirm the wave picture, and many physicists hailed Maxwell's theory as one of the crowning achievements of 19th century physics. And yet, when physicists tried to apply this theory to one of the simplest imaginable situations, how hot objects radiate, it broke in a spectacular way. The problem was posed in a very concrete form. Consider a hollow cavity with opaque walls, heated and then left alone so the temperature is uniform and stable throughout. If you now create a small hole in the side, the radiation that leaks out has a very specific and universal character. The spectrum depends only on the temperature, not on the material or the shape of the cavity. Experimentally, you measure a quantity called the spectral energy density, which represents the energy per unit volume per unit frequency. When you plot frequency on the x-axis and spectral energy density on the y-axis, you get a very distinctive curve. The challenge at the turn of the century was to find a theoretical law that reproduces this curve. There were already some important empirical clues. It was known that if you increase the temperature, the peak of the curve shifts to higher frequencies, and if you reduce the temperature, the peak shifts to lower frequencies. And furthermore, as temperature increases, the area under the curve increases, signifying an increase in the total energy density. This matches everyday experience. If you put a piece of metal into a hot furnace, it glows first a dull red, then a brighter orange and yellow, and then a brilliant white, as the dominant radiation shifts to higher and higher frequencies. But how could all of this be explained using the best known laws of physics of the day? Well, the natural place to turn was Maxwell's theory of electromagnetic radiation, together with the highly successful laws of thermodynamics and statistical mechanics. But when you do this in the most straightforward way, you immediately run into trouble. To see why, imagine the radiation trapped inside the cavity. Only certain wavelengths can fit, those for which an integer number of half wavelengths fit between the walls, so only certain frequencies are allowed. But there is no limit to how small the wavelength can be, and therefore no limit to how high the frequency can be. The allowed frequencies are discrete, but they extend upward without bound. And if you do the calculation, you find that the number of electromagnetic modes per unit volume in a small frequency range between f and f plus df is given by the following expression. Now, don't worry too much about where this comes from. For those interested, I've made another video looking at that. But for our purposes, the crucial feature is the dependence on frequency. The number of available modes grows like f squared. In other words, the higher the frequency, the more and more independent standing wave patterns there are that exist. On its own, this might not sound like a problem. However, the real difficulty enters when you add in statistical thermodynamics. You see, according to the well-established equipartition theorem, each mode is assigned the same average energy, which is equal to Boltzmann's constant multiplied by the temperature, and completely independent of the frequency of the mode. And from here, the calculation is conceptually straightforward. You simply count the number of modes within a small frequency range, which we have already said is equal to 8 pi f squared over c cubed times df, and then you multiply by the average energy per mode, which statistical thermodynamics tells us is equal to kT. And this then gives you the energy density within this frequency range. And so we end up with the following expression. And then if you cancel the df's from both sides, we end up with the following equation for the spectral energy density as predicted by Maxwell's theory and classical statistical thermodynamics. Now, at this stage, you may not think that there is a problem. However, if you plot the energy density as a function of frequency, you find that at high frequencies it grows quadratically without bound. And if you then try to compute the total energy density by integrating over all frequencies, that is, by calculating the area under the curve, the integral does not converge, it diverges. Classical physics is therefore predicting something impossible. It's saying that radiation in thermal equilibrium should contain an infinite amount of energy. Clearly, something has gone badly wrong. This failure became known as the ultraviolet catastrophe, because the divergence shows up most dramatically at the high-frequency ultraviolet end of the spectrum. And yet, at very low frequencies, if we overlay the experimental results, we see that this very same calculation fits the data very well. So classical theory is not simply wrong everywhere, it's wrong in a very specific and a very deep way, and only once you push it to sufficiently high frequencies. But there was another crucial clue. The physicist Wilhelm Wien had found a law that describes the spectrum extremely well at high frequencies. He found in this regime the data are well fitted by an expression for the energy density of the following form, where F is the frequency, T the temperature, and A and B are constants. If you plot this function and compare it with the experimental curve, you see that the agreement with experiment is excellent when you go to very high frequencies where the curves overlap. However, if you go to low frequencies, the function clearly does not match the experimental data. And so this was the problem facing physicists. Two partial answers, one that fitted data at low frequencies and one that fitted data at high frequencies, and a set of experimental data connecting the two extremes that demanded one unified law. And that law was found by Max Planck in 1900. Planck proposed a single formula that smoothly interpolated between those two regimes. At low frequencies it reduced to the classical result, and at high frequencies it reduced to Wien's law. And when plotted, it beautifully fitted the experimental data across the entire spectrum with extraordinary precision. But how did he do it? Well, if you recall, the problem with the classical approach had been that the number of cavity modes grew with the square of the frequency, and because every frequency mode was assigned the same average energy, the net effect was an energy density that grew quadratically in frequency, leading to the ultraviolet catastrophe. Planck solved this problem by showing that if, instead of every mode being assigned the same average energy, the average energy of the modes fell off at high frequency, then this effect could counteract the quadratic growth of the number of modes, leading to the characteristic curve observed in experiment. To get this result, Planck did something extraordinary. He later described it as an act of desperation. He assumed that energy could only be exchanged in discrete amounts, in integer multiples of hf, where h is what is now called Planck's constant. In other words, each quantum carried energy hf. But conceptually, this left an important question open. Planck still regarded the electromagnetic field itself as a continuous wave. The quantization, in his view, was a property of the interaction between matter and radiation, not necessarily a property of the radiation itself. And so by 1905, physicists had a strange situation. They had a formula that worked extremely well for describing the energy density profile of cavity radiation, and they had a calculation that relied on energy being exchanged in discrete chunks or quanta. But it was still unclear what, physically, this discreteness was telling them. For example, was it a property of matter, a property of radiation, or just a calculational trick? Planck had solved the problem of the spectrum, but he had not yet solved the problem of interpretation. Before we get back to Einstein and the quantization of light, a quick note about something I've been building alongside this series, the Physics Explained website. One thing I've noticed while working on it is how much presentation and style matter. When the ideas are complicated, the structure needs to be simple. That's why I've been using Squarespace. It gives me clean layouts, consistent typography, and pages that work properly on different screens, without me having to micromanage any of it. I'm not fighting formatting, I can just focus on building the site the way I want it to work. It also means I can put diagrams, visuals, and longer explanations in one place and have it feel coherent rather than bolted together. The result is a site that's calm, readable, and focused on the content. If you want to try it, go to squarespace.com for a free trial, and when you're ready to launch, head to squarespace.com/physicsexplained to get 10% off your first website or domain. And this is exactly the point that Einstein enters the story. In June 1905, he published a paper that he had described as very revolutionary under the imposing title On a Heuristic Viewpoint Concerning the Production and Transformation of Light. Today it's usually remembered as the Photoelectric effect paper, but that label is deeply misleading. The paper does not begin with metals, electrons, or experiments. Rather, Einstein opens his paper by drawing attention to a deep structural mismatch inside physics itself. On the one hand, there is the theory of matter. For gases and other ponderable bodies, the state of a system is specified by a finite set of discrete quantities, the positions and velocities of atoms and molecules. On the other hand, there is Maxwell's theory of electromagnetism. There, the state of the system is not given by a list of particles, but by continuous fields, smooth functions defined at every point in space. In Einstein's own words, there is a profound formal distinction between these two ways of describing nature. This difference had not seemed troubling as long as both theories worked in their own domains, but the blackbody radiation problem had changed that. And so Einstein decided to proceed without assuming a picture of the creation and propagation of radiation. Instead of guessing what light is made of, he would try to extract that information from the most reliable facts available. And those facts came from two sources. The first was the experimentally established form of the blackbody radiation spectrum, and the second was the most general and powerful principle available for systems in equilibrium, the second law of thermodynamics, and more specifically, the statistical interpretation of the second law that had been put forward by Ludwig Boltzmann. Boltzmann's key insight was that entropy measures how many microscopic possibilities correspond to the same macroscopic description. For example, there are many more ways to arrange red and blue paint pigments so that from a macroscopic perspective the paint looks purple than there are ways to arrange them so that the red and blue remain in separated layers. It's why it's unimaginably unlikely that stirring paint will cause it to unmix. And from the perspective of a gas, it's why a fixed number of particles occupying a smaller region of space has a lower entropy than the same number of particles spread throughout a larger volume. There are simply more microscopic configurations available in the larger volume for the same number of particles and the same temperature. But in Maxwell's theory, radiation is not a gas of molecules. It's a continuous electromagnetic field described by smooth functions defined at every point in space and time. There are no obvious particles whose arrangements you could count in the way that you can for a material gas. And so the question becomes unavoidable. If radiation really does obey the laws of thermodynamics, then what exactly is that entropy counting? Einstein's first line of attack is to link the energy density of cavity radiation with a corresponding entropy density of radiation. We know from experiment that at temperature T, the radiation in a cavity has a specific energy density curve, a precise map of how the energy is spread across different frequencies. We write this energy density as ρ of Ft, and then to get the total energy, you integrate ρ over all frequencies to get the total energy density, and then multiply by the cavity volume V to get the total energy. But thermodynamics tells us that the very same equilibrium state must also have a definite total entropy. So Einstein's first conceptual move is to introduce a matching curve, an entropy density sigma of Ft, which tells you how the entropy is distributed across the spectrum. And we can then obtain the total entropy by finding the area under the curve, by integrating over all frequencies and then multiplying by the volume of the cavity. And because these two curves are describing the same physical state of the field, it's natural to expect a direct link between them. In other words, you can think of sigma as being determined by rho for a given frequency, once the thermodynamic relation is specified. Now, notice that as the temperature changes, the energy curve shifts, and the entropy curve has to shift with it. Einstein's starting question is what exact relationship ties the energy density, entropy density, and the temperature together? So, how on earth do you answer that? Well, up to now we've been looking at the spectrum as one smooth curve. But Einstein's next move is to turn that smooth curve into something you can reason about, like a thermodynamic system made of parts. So imagine we slice the frequency axis into lots of very narrow bands, each one a tiny interval of width df. Each band is like a little subsystem of the radiation field. It holds a small amount of energy, and it contributes a small amount of entropy. And here's the key assumption that makes the whole strategy work. For a given band, the entropy it contributes depends only on how much energy sits in that band, and on the frequency of the band, and the total entropy is then just the sum over all the bands. More specifically, in a cavity of volume V, the energy contained in a narrow band centered on frequency f is equal to V times rho df, and the entropy contained by that same band is equal to V times sigma df. And it then follows that the total energy and total entropy are simply given by summing over all the bands. Now the key idea. You hold the volume fixed and the total energy fixed as well, but now imagine that you are allowed to reshuffle that energy between different frequency bands. Depending on how the same energy is distributed, both the entropy distribution and the total entropy itself changes. And you can see from the plot that the distribution we call thermal equilibrium is simply the one that makes the total entropy as large as possible. Now the question is, how do we turn that global statement about entropy maximization into something that we can actually use? How do we extract a concrete mathematical condition? Well, we begin by realizing that if the spectrum really is at equilibrium, then no allowed infinitesimal redistribution of energy between frequency bands can increase the total entropy. If such a redistribution existed, then the system would not yet be in equilibrium, and it would spontaneously move in that direction. So let's now consider the simplest possible reshuffle. Pick two narrow frequency bands, one near f1 and one near f2, and then transfer a tiny amount of energy delta E from band 2 to band 1. The total energy stays the same because we've only moved energy around, but the total entropy can generally change. Because the entropy of each band depends on how much energy it contains, a small change in energy produces, to first order, a change in entropy given by the local gradient of entropy as a function of energy. In other words, if band 1 gains energy delta E, its entropy change is given by the gradient ds1 by de1 multiplied by delta E. Then, if band 2 loses the same amount of energy, its entropy change is again given by the gradient at frequency 2 multiplied by minus delta E. If we then add these together, the total change in entropy from this swap will be equal to delta S1 plus delta S2, which gives the following expression, where we factored out delta E. Now comes the crucial point. The only way that the first order change in entropy is equal to 0, given a non-zero change in energy delta E, is if the term inside the bracket is 0. If this were not the case, then there would be some direction of energy transfer that increases the entropy, which means the system was not yet at equilibrium. Or to put this another way, at thermal equilibrium we must have that ds1 by de1 equals ds2 by de2. But now note that there was nothing special about the two bands we chose to exchange energy between. We could have picked any pair. So this isn't just a statement about band 1 and band 2, it's a statement about every band in the spectrum. The only way that can be true is if the entropy gained per unit energy added is the same across all bands. In other words, if ds by dE is equal to the same constant in every band. So equilibrium forces a universal conclusion. In thermal equilibrium, every frequency band has the same entropy gained per unit energy added. There is no band that is a better place to put energy than any other. Otherwise, the system could still increase its entropy by shifting energy around. Now, notice something important. This quantity that we've just been forced to equalize across bands, ds by dE, is not unfamiliar. In thermodynamics, for any system at fixed volume, the temperature is defined by the rate of change of entropy with respect to energy, according to the relation ds by dE, with V held constant, is equal to 1 over T. So the condition we've derived has a clear physical meaning. It's simply the statement that all parts of the system are at the same temperature. If two bands had different values of ds by dE, they would effectively be at different temperatures, and energy would flow between them until those temperatures equalized. Therefore, if the radiation within the volume is in thermal equilibrium at temperature T, each narrow frequency band must satisfy the relation ds band by dE band is equal to 1 over T. Our next task is to turn this from a discrete expression relating to each energy band to a general statement relating the energy and entropy densities. Now, as we've already seen, for a frequency band of width df centered at frequency f in a cavity of volume V, the entropy and energy within the band are given by the following expressions. And so if we substitute these expressions into our derivative expression and then use the chain rule, we end up with d sigma by d rho, and this is equal to 1 over T. And so we see that the equilibrium condition becomes d sigma by d rho equals 1 over T. And this is exactly the bridge that Einstein needed. A purely thermodynamic relation that links the entropy content of radiation to its energy distribution. And this is before assuming anything at all about the microscopic nature of light. Now Einstein makes his next move. He wants to actually calculate the entropy density function by using an explicit expression for the energy density in a regime where he knows that classical physics breaks down, namely the high frequency regime. And for this reason, he chooses Wien's radiation law, which at the time was known to describe blackbody radiation accurately at high frequencies and low radiation densities, precisely the regime where the classical approach fails most badly. The strategy is now straightforward. Thermodynamics tells us that the derivative d sigma by d rho is equal to 1 over T, and so the first step is to use Wien's law to find an expression for 1 over T. Firstly, we rearrange the equation slightly, and then take the logarithm of both sides and end up with the following expression. If we then divide both sides by bf, we find the following expression for 1 over T. Now, if we insert this directly into the thermodynamic relation, we end up with the following differential equation. And we now wish to solve this for the entropy density sigma. To do that, we simply need to integrate with respect to the energy density rho, and if you perform the integration, you end up with the following expression, where c is an integration constant. Einstein fixes the constant by a simple physical requirement. If there is no radiation present, there should be no entropy. And we see that in the limit that rho goes to 0, sigma goes to 0, provided we choose c equal to 0. And so we're left with the following expression for the entropy density. And this is precisely the expression that Einstein derives from the Wien expression for the energy density. Einstein's next move is to specialize to a very simple case. He considers a narrow, almost monochromatic slice of radiation confined to a tiny frequency interval between f and f plus df. If we then suppose that this slice carries a total energy E and occupies a volume V, then, as before, we can write the energy as V times rho times df. And if we rearrange this, we can write that ρ is equal to E divided by V times dF. Now, the entropy carried by this same slice is, as noted earlier, equal to V times sigma times dF. So what we can now do is substitute our expression for ρ into our expression for sigma, and then finally sub this into our expression for the total entropy, and we end up with the following relation. And this is what Einstein wanted, an expression for the entropy of a narrow, almost monochromatic slice of radiation carrying total energy E in a volume V. Now Einstein asks the following question: how does the entropy change when you change the volume? Can we use the expression that we've just derived to answer this question? To begin with, let's simplify the expression by defining A equals E divided by AF cubed dF, in which case the entropy expression then neatens up slightly. And we can then use the properties of logarithms to rewrite this in an equivalent form. Next, we imagine that the radiation occupies an initial volume V0, in which case the entropy S of V0 takes the following form. If we then imagine a final volume V, then we can write S of V in the following form. It then follows that the change in entropy delta S can be written as S of V minus S of V0, and if we then sub in our expressions, the common terms cancel and we end up with an expression in terms of V and V0. We can then combine these two logarithm terms and we arrive at our final compact result. And this is the result Einstein wants. Notice that the entropy change depends on the volume only through a logarithm of the ratio V over V0. That dependence is not generic, it's highly distinctive. In fact, it's exactly the same volume dependence that one finds for an ideal gas of independent particles. For a gas with fixed energy and fixed particle number, expanding from V0 to V, the entropy change is proportional to the logarithm of V over V0. And here we see that without assuming particles, without assuming anything at all about the microscopic nature of light, Einstein has found that monochromatic radiation in the Wien regime behaves thermodynamically as if it were a gas of independent entities. And notice how little went into this conclusion. No model of the particulate nature of light, no quantized oscillators, no speculative mechanics. In fact, there were just three inputs: the empirical Wien law, the thermodynamic definition of equilibrium, and the requirement that entropy behaves like entropy should, that it's additive. Yet out comes a result with a very sharp signature. In the high-frequency regime that Einstein is investigating, the radiation behaves under a change in volume in precisely the same way as a collection of independent, discrete entities. This is not yet a proof, it's not yet a statement about what light is, but it's a powerful clue. Thermodynamically, radiation in this regime is behaving as though it were countable. Einstein now takes the next conceptual step. He draws on Ludwig Boltzmann's insight that entropy is related to the number of microscopic configurations compatible with the same macroscopic state. For example, in a gas, many different molecular arrangements can correspond to the same macroscopic properties, the same temperature, pressure, and volume. Boltzmann made this idea precise. If we let W of V be the number of microstates compatible with radiation occupying volume V, and W of V0 the number of microstates compatible with the same radiation occupying volume V0, then, according to Boltzmann's principle, the entropy difference between these two macrostates is equal to Boltzmann's constant multiplied by the logarithm of the ratio of the corresponding microstate counts. And so we now have two expressions for the entropy change. And Einstein said that if we take Boltzmann's idea seriously, then we should be able to equate these two expressions. So let's do that and then divide both sides by Boltzmann's constant, and then we can use the properties of logarithms to rewrite the right-hand side. And then finally, if we exponentiate both sides, we find that W of V divided by W of V0 is equal to V over V0 raised to the power of E over KBF. Now, Einstein's next move is to find an expression for the left-hand side with minimal assumptions about the underlying microscopic system. To do this, Einstein imagines a volume V0 containing n independently moving points. He assumes that no region is preferred over any other, so at a randomly chosen instant each point is equally likely to be anywhere inside the volume V0. Next, imagine a subvolume V. The question is, what is the probability that at that instant all n points happen to lie inside V? Well, for a single point, the probability of being inside V is simply equal to the volume ratio V divided by V0. Then, because the points move independently, the probability that all n are simultaneously inside V is the product of the individual probabilities. Since there are n particles, this will be equal to V over V0 raised to the power of n. Now, here's the key point. In Boltzmann's language, this probability can be thought of as a relative microstate count equal to the ratio of the number of microstates corresponding to volume V and V0 respectively. And so, if we then equate the two expressions for the probability, we end up with the following expression. Now, we can compare this with the result we derived earlier for radiation, and we notice something quite remarkable. The structure of the two expressions is identical, both involving a power of the same volume ratio V over V0. In the first case, the expression relates to n independent points, whereas in the second case, it relates to monochromatic radiation of energy E. And in the case of the n independent points, we know exactly what the exponent means. It counts how many independent points the system contains. And so, by direct analogy, the exponent appearing in the radiation expression must be playing the same role. So here Einstein makes his interpretive step. In his words, monochromatic radiation in the Wien regime behaves as if it consisted of independent energy quanta. In other words, the radiation is behaving as though it were comprised of an effective number of independent quanta given by the relation n equals E divided by kBF, just by comparing the two exponents, where here nf refers to the number of independent quanta. And we can take this idea even further and determine the energy of a single quantum. If the total energy E is carried by nf independent quanta, and we call the energy of each quantum epsilon, then by definition the total energy E will be equal to the number of quanta multiplied by the energy of one quantum. And if we then rearrange this expression for epsilon and sub in the expression we derived for n, we see that the total energy of one quantum is given by kBF. Now, in its current form, this may not look familiar, but there is one last trick we can use. If you recall, we started from Wien's law, which contained the unspecified constant B. Now, it turns out that we can actually specify this constant by comparing where the Wien law overlaps with the Planck law at high frequency. And we find that in modern form, the constant B is equal to Planck's constant divided by Boltzmann's constant. And so, if we now sub this into our equation for epsilon and cancel off the k's, we end up with the simple and elegant result that the energy of a single quantum is equal to Planck's constant multiplied by the frequency of the radiation. And this is the punchline. This is Einstein's incredible realization. In the high-frequency Wien regime, radiation behaves thermodynamically as if it consists of independent quanta, each carrying energy proportional to its frequency, hf. And it's worth pausing to reflect on what's just happened. Nowhere in this argument did we assume light quanta at the start. We didn't build them in. We began with thermodynamics, with an empirical radiation law, and with Boltzmann's relation between entropy and probability, and we followed the logic where it led. The quantum idea has not been assumed, it has been extracted from the thermodynamic behaviour. And it immediately raises a question. What exactly should we make of it? Is this just an analogy, or a statement about what light really is? Well, part of Einstein's genius is knowing when to pay attention to something, and so Einstein proceeds to treat the idea that light is comprised of independent quanta as a serious hypothesis, and to look for physical processes where the idea would lead to clear, testable consequences. One especially striking case was already well known: the photoelectric effect. If you shine light onto a clean metal surface and then gradually increase its frequency from red through yellow and blue towards the ultraviolet part of the spectrum, nothing initially happens until a sharp threshold is crossed. Above that threshold, electrons are emitted, and the higher the frequency, the greater the maximum kinetic energy of those emitted electrons. But here's the point: below the threshold, no electrons are emitted at all, no matter how long you wait or how intense the light. And that is the startling thing. The threshold cannot be brute forced by brightness. If the frequency is below the threshold, then no matter how intense the light, not a single electron is emitted. But if the frequency is above the threshold, then increasing the intensity of the light increases the number of emitted electrons each second, without increasing their maximum kinetic energy. Only the frequency of the light has an effect on the maximum kinetic energy. The problem was, from the perspective of classical electromagnetic wave theory, none of this makes sense. For a wave, intensity is simply the rate at which energy is delivered to the surface. And so in the classical picture, this energy is transferred continuously to an electron, and the electron's energy should gradually increase until it has enough energy to escape from the metal. From the wave perspective, increasing the intensity just means increasing the amplitude of the wave, and therefore increasing the rate at which energy is delivered to the electron. The problem is, according to the wave picture, even low frequency light should eventually transfer enough energy to cause electrons to be ejected from the metal. But this is not what is observed. If the frequency remains below a sharp threshold, no electrons are ever emitted, no matter how intense the light. And this directly contradicts the classical wave theory of light. And furthermore, you can turn this classical intuition into a concrete testable prediction. For example, suppose a 1 watt light source is placed 3 meters from a potassium surface. At a distance of 3 meters, this radiation will be spread uniformly over a sphere of radius 3 meters, and therefore the intensity at the surface can be calculated using the fact that intensity is equal to power per unit area, and this will be equal to 1 watt divided by the surface area of a 3 meter radius sphere. And when you calculate this, you find a value of 8.8 times 10 to the minus 3 watts per square meter. Now imagine that a single electron absorbs energy from a tiny patch of the wavefront of atomic size with radius 5 times 10 to the minus 11 meters. The area of this patch will be equal to pi r squared, which is equal to 7.85 times 10 to the minus 21 meters squared. We can then calculate the power intercepted by this patch by multiplying the intensity by the cross-sectional area that we just calculated. And when we do this, we find a result of 6.9 times 10 to the minus 23 watts, which corresponds to an energy transfer of 6.9 times 10 to the minus 23 joules per second to this patch. Now, given that the work function of potassium is about 2.3 electron volts, which is roughly 3.7 times 10 to the minus 19 joules, this tells us how much energy the electron requires to escape from the surface. And given that we also know the energy transferred per second by the light to the electron, we can calculate the time required for a single electron to accumulate enough energy to escape. This is equal to the work function divided by the power. And when we sub in the numbers, we find a value of 5.4 times 10 to the 3 seconds, which is about 90 minutes. And so, according to the classical picture, you would expect a slow, gradual build-up before emission, and no sharp frequency cutoff at all, just longer and longer waiting times at lower frequencies. But the experiment does something completely different. Above the threshold, electrons are emitted essentially immediately, Below the threshold, they are never emitted, no matter how long you wait or how intense the light is. The classical wave picture gets the key features completely wrong. However, Einstein's quantum hypothesis cuts straight through the puzzle. Based on his entropy reasoning, Einstein imagines that light consists of a stream of fundamental particles that we now call photons, with each photon carrying an energy equal to Planck's constant multiplied by the frequency. So how does this help with the photoelectric effect? Well, Einstein's idea is simple. He assumes that the energy of a photon can be transferred to a single electron in a one-to-one interaction. If we imagine that a single electron requires a certain minimum amount of energy, phi, to escape the metal, and imagine that this electron gains energy equal to hf by absorbing a photon, then what's left over appears as the kinetic energy of the electron. And so the fastest electrons should therefore satisfy the relation K max equals hf minus phi. And this simple idea immediately explains the experimental facts. It explains why, if the frequency is not high enough, then individual photons will not have enough energy to overcome the work function of the metal, and therefore no electrons will be emitted. It also explains how the maximum kinetic energy depends only on the frequency and not on the intensity. And it also explains that from the photon perspective, light intensity simply relates to how many photons per second are incident on the surface. Provided the frequency is high enough, if you double the intensity, you double the number of photons and therefore the number of electrons emitted per second. And all of this can be tested experimentally. By applying a voltage across the metal plate, you can make it positively charged and cause the escaping electrons to be attracted back. And if you increase this voltage until even the fastest electrons are just prevented from leaving the surface, then the maximum possible kinetic energy has gone into doing work against the potential difference. At that point, we can write that the work done, which is equal to the electron charge times the voltage, is equal to the maximum kinetic energy. And here Vs is called the stopping potential. If we then combine this with Einstein's photoelectric equation, we find that E times Vs is equal to hf minus phi. And then, if we divide both sides by the electric charge E, we find that Vs is equal to h over E times f minus phi over E. Now, this is a very enticing equation because it has the exact form of a linear straight line equation. More specifically, if you vary the frequency of the incident radiation and measure the stopping potential at each frequency, and then plot Vs against f, the result should be a straight line with a gradient equal to h over E, and an intercept from which the work function of the material can be determined. That's a very sharp prediction. It doesn't just tell you the shape of the graph, it fixes the exact value of the gradient. This isn't a vague suggestion, it's a concrete testable claim. And in 1905, Einstein published his result under the title On a Heuristic Viewpoint Concerning the Production and Transformation of Light, setting out the thermodynamic reasoning that we followed in this video and presenting the photoelectric relation itself. All that remained was experimental verification, and it would take nearly a decade of painstaking work before the verdict was clear. The decisive experiments were carried out by Robert Millikan. By 1915 he had obtained the crucial results, and in his 1916 paper, A Direct Photoelectric Determination of Planck's H, he showed that the stopping potential really does increase linearly with frequency, and that the slope gives Planck's constant. The agreement with Einstein's equation was striking. And yet acceptance of the underlying idea was slow. Millikan called the idea a bold, not to say reckless, hypothesis that flies in the face of the thoroughly established facts of interference. He spent years, nearly a decade, testing Einstein's 1905 equation, and in the end he had to accept its unambiguous experimental verification, even though he still had doubts about the theory behind it. And that hesitation wasn't his alone. Even some of Einstein's strongest supporters treated the light quantum idea with caution. For example, when Max Planck recommended Einstein for the Prussian Academy, he praised his brilliance, but suggested that if Einstein sometimes missed the mark, as for example in his hypothesis of light quanta, that could hardly be held against him. The equation was accepted, the picture behind it was not, and that distinction would linger for years. When Einstein received the 1921 Nobel Prize, the citation fixed on what no one could dispute: for his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect. The experiment came first, the interpretation followed slowly and reluctantly. Einstein's light quantum wasn't accepted because it was fashionable or because it fit comfortably with the old wave picture of light. It was accepted because experiment forced physics to confront it. Millikan confirmed the photoelectric law. Compton's scattering then showed that light behaves as quanta, carrying energy and momentum. By the mid-1920s, the photon had become unavoidable, and today we can detect single photons one by one. That is Einstein's genius, not just in proposing something radical, but in recognising which clues mattered and following them all the way through to their logical conclusion. And that is where we will end for today. And as always, a massive thank you to all my patrons, and a special shout out to the following who have been incredibly generous with their support. Thank you so much. I couldn't do it without you.